everyone. This is Chris with the Ancient Scholar, and today, in celebration of Valentine's Day, I'd like to talk about attraction. Obviously a certain type of attraction, and that attraction is going to be the Coulombic attraction that an electron and the nucleus of an atom have, or more accurately, the positively charged proton and the negatively charged electron. And we know that in the physical world, generally opposites are going to attract each other, and that certainly is the case when it comes to electrons and protons, electrons and nuclei. That's obviously what makes atoms. So I think that a very intuitive and very natural question from all of this would be, well, if, and we'll just draw a little picture of that, if I have a nucleus that's positively charged and I have an electron out here that is negatively charged, clearly there is going to be some attraction here. And it simply would make sense intuitively, I think, if we ask the question, well, what is stopping these guys from coming together? They're attracted to each other. You know, we see you use a magnet, and ferromagnetic materials attracted to the magnet, they come together and slap together and attach onto one another. So it would make perfect sense that in an atom, that an electron and the nucleus would come together, and eventually the electron would kind of smash into that, the nucleus. Obviously that would be kind of bad news for physical reality, because all of the atoms in our world and our bodies would be annihilating one another, and that certainly probably wouldn't be the greatest thing to have happen. And clearly it doesn't happen a whole lot, or we would be in real big trouble. So let's just go ahead and look at this classically. We knew Maxwell's equations and Faraday and that, you know, we knew that if I have something with charge, something that's charged, and you know, we change its acceleration, or velocity acts upon it, and it moves, what happens is it releases its charge. And that's kind of the basic concept behind radios. We have a charge, and we move the charge around, and it sends out energy. And clearly that is even more bad news for the human race and everything living on the earth, because if I have a nucleus and I have an electron that's orbiting around that nucleus, because that's what we thought at one point, is that, you know, obviously the electron orbits around like a planet. Well, we knew a long time ago that if that happened, you know, that electron is going to give off energy, and it's going to kind of basically do a death spiral. It's going to lose energy, and as it does, it's going to spiral in and smash into the nucleus, and all will be lost for the universe, or at least the universe when it comes to you know, baryonic and leptonic matter and all that kind of stuff. It's certainly not great for the prospect of life as we know it. Clearly this doesn't really happen a whole lot, or we would certainly be in more trouble. So what really is going on here? And what's going on is actually more complicated than I could ever really explain in a 10 or 15 minute video. So I'm gonna kind of revert to some classical analogies that aren't completely or totally accurate, but at least they will get the flavor across of what's going on with this business here. And so the first thing, historically, we knew that Max Planck, to explain how objects, black body objects, and objects that is heated, how it gives off radiation. Obviously that's just light. he came up with a constant known as H, or 6.626 times 10 to the negative 34 joule seconds. To explain this, because before this we thought that energy could be given off continuously, and if that really was the case, that it was continuous, and that you could take on any arbitrary value of energy, you know, we basically have infinite amounts of energy in our black bodies, and you know, if we lit a burner on the stove and it heated up, it just keep going, and it would be kind of a disaster. And they actually called it, excuse me, they actually called it somewhat of a catastrophe back then. And he really Planck in about 1900, 1905 kind of figured out that energy, he didn't realize it at the time, but they came to realize that energy was quantized, or very discrete, and it actually came in little packets called quanta, and the most fundamental, the smallest unit of energy in existence is this H, Planck's constant, or 6.626 times 10 to the negative 34 joule seconds. I believe this was in 1900. In 1905, of course, Einstein solved basically the ultraviolet catastrophe by explaining the photoelectric effect, how electrons are emitted from certain metals when we shine ultraviolet light on them. Using Einstein basically said, look, all of light energy is defined by this quanta, or this H. That all of energy is defined by these little packets. And then a little later on, Bohr, in about 1913, Niels Bohr used this whole quantization phenomenon, and he said, look, I have a nucleus, and because the energy of electrons must be quantized, or must be discrete, the electrons can orbit, but they can only orbit in certain discrete levels of energy around the nucleus. The lower energy is closer, the higher energy is further away. And these levels of energy, of course, were n equals 1, n equals 2, n equals 3, and so on and so forth. And he put forth what's known as the planetary model, where these electrons orbited, and the reason that they didn't smash into the nucleus and lose energy is because they were quantized and they were contained within this level of energy, and they couldn't go anywhere. And Niels Bohr didn't really expand on all of the other questions. He said, look, this is how it is. They're confined to these levels of energy. They're quantized. That's just the way it is. And of course, n equals 1. He said that the distance from the nucleus was about 0.53 angstroms, and that became known as A naught, or the Bohr radius, which is still something we use today in calculations. Okay, well, this described a hydrogen atom fairly well, but there were just lots of things going on that couldn't be described by this model. And then finally, to get kind of to the point of the question, or not finally, it certainly wasn't the end of it, Werner Heisenberg came along and realized, well, I should back up a little bit. Before Bohr, a guy by the name of Louis de Broglie realized that matter, or a little after Bohr, I apologize, matter can take on wave-like properties. So all the matter that we know of also has a wavelength, and obviously we're not really aware of that wavelength in our large macroscopic world, but it becomes very obvious in the microscopic world. And hence the term matter wave, and that's why we have to treat certain things as waves sometimes, and this is why we treat electrons as waves sometimes, and particles other times, even though they're really not either, as far as I can tell. They're just something that we can look at as a particle or a wave depending on the question we ask. Okay, so kind of get back to the point, Heisenberg came up with the uncertainty principle. And we'll just talk about that real quick. That uncertainty principle is delta x times delta p is greater than or equal to h bar over 2. H bar is just h over 2 pi. So basically what he said is, or what we found is, that the uncertainty in position multiplied by the uncertainty in momentum has to be greater than or equal to h bar over 2 pi. That is as accurate as we can get. So basically what this says is, I cannot know the position, I cannot know where something is or where it's going with infinite accuracy at the same time, or with arbitrary accuracy. I can't know that at the same time. If I know the position very well, I cannot know where it's going very well. Likewise, if I know where it's going very well, I cannot know its exact position very well. And the uncertainty principle is what kind of led to the whole probabilistic nature of quantum mechanics. You know, everything is probability now because we can't know for certain. We cannot arbitrarily know. And that's my first point, is that if an electron actually did go into the nucleus, you know, it's just a tiny little area, you know, electron smashed in the nucleus, and we knew that it was in there, blended in with the nucleus, well, that would be a violation of the uncertainty principle, first of all, because the electron, you know, we can't really know that. So that's probably the easiest answer, one of the answers. And another way to look at it is, you know, look, the electron is very probabilistic, right? We really don't know where it is. Its position can theoretically be anywhere in the universe, and it's just most probable positions, of course, are those little orbitals that we find out. And certainly that, you know, that's part of it. Is, you know, look, it's kind of a fuzzy thing. It kind of is here and there and everywhere, and we don't really have a good handle on where it is. So it's really not even a great question in some ways to ask, because it's so indeterministic. And certainly there is a probability that maybe an electron can be in the nucleus, but it's certainly not very likely. And I think another way of looking at it is, if I have my nucleus, the little guy is on the way out. I have my nucleus here, and again, we can't look at these things as particles. I'm going to draw them as particles because it's easier to see. But in a stable atom, a hydrogen atom, with no influence around, the energy of that atom isn't going to change. The total energy, that's conservation of energy, right? I can't pull it out of my butt. It's not going to get more or less just out of nowhere. Okay, so the energy in an atom that's left alone isn't going to change. Well, what happens is, as an electron moves closer to the nucleus, its potential energy, okay, its potential energy is going to decrease. Well, I can't, where does the energy go though, right? I can't create or destroy this energy. So if my potential energy is decreasing as the electron is getting closer to the nucleus, what is happening? What is happening to the kinetic energy? Well, the kinetic energy must be increasing, right? It's just moving faster. So we kind of have this situation where the electron gets closer and its potential energy is basically decreasing toward infinity, which means its kinetic energy has to increase toward infinity. And obviously, the closer it gets, eventually at some point the kinetic energy is going to win out and the electron is going to move off somewhere further away from the nucleus. Kind of like pulling a big spring in, and at some point it just goes boom and flies off. Sort of the similar analogy here. And this is the analogy that kind of makes a lot of sense to me, is, oh, okay, you know, the kinetic energy increases to infinity and the electron, you know, there's this tug of war that neither side can win, so the electron really doesn't have a great chance of getting into the nucleus. Hopefully that makes a little bit intuitive sense. And then just to kind of wrap things up, electrons can occasionally crash into the nucleus in very large, unstable atoms, where maybe you have an unscreened electron and it crashes in, and that atom, of course, then, you know, falls apart, and there's a very specific type of nuclear decay that occurs as a result of that. And again, you know, that can occur in very unstable atoms, very unstable isotopes, and so on and so forth. But we don't really see this occurring in the day-to-day atoms that we need, and certainly not on a large scale, or we wouldn't be here. So hopefully that made some sense, and hopefully you guys have a little intuition there. Thanks, guys. Take care.